Hello and welcome. This is the Science Channel for Sleep. If this is your first time here, you have found a quiet place, a space designed for rest, for gentle learning, and for letting the mind settle into something calm and unhurried as sleep begins to arrive. And if you have been here before, it is always good to have you back. Take a moment right now to settle in. Adjust your pillow. Pull your blanket a little closer. Let your body relax into wherever you are resting tonight. There is nothing you need to do in this hour except listen. Whatever filled your day, the tasks, the questions, the small and large concerns, all of it can wait until morning. This time is yours. Before we begin, if you enjoy this kind of calm, educational content, a like and a subscribe are always appreciated. They help other people who are looking for exactly this kind of quiet place to wind down find their way here. And if you have already subscribed, thank you sincerely. Now, where are you tonight? What time is it there, wherever you are listening from? Are you settling in early? The evening still young outside your window? Or is it late, the house quiet, the world around you still and dark? It is always interesting discovering where listeners are tuning in from around the world. Some of you may be in the middle of a cold winter night. Others may be listening in a warm evening in a different season entirely. Wherever you are, whatever the hour, this space is for you. Tonight, we are going to talk about one of the most celebrated and most frequently misunderstood ideas in the history of science. We are going to talk about Einstein's theory of relativity. And before we go any further, there is one thing worth saying clearly, right at the beginning, because it addresses the most common misunderstanding about the theory. Relativity does not mean that everything is relative. It does not mean that truth depends on your point of view, or that there are no absolutes in the universe. In fact, the theory does almost the opposite of that. Einstein's relativity identifies what is absolute, what is invariant, what is the same for every observer in the universe, regardless of how they are moving or where they are. The speed of light is the same for everyone. The laws of physics are the same for everyone. These are the things the theory insists upon. What is relative, what does change depending on your perspective, is the measurement of time and space. And those changes, which follow inevitably from the absolute constancy of the speed of light, turn out to reveal a universe that is far more interesting than the one classical physics described. There are two theories that travel under the name of relativity. Special relativity, published in 1905, deals with objects moving at constant velocities, particularly at speeds approaching the speed of light. General relativity, published a decade later in 1915, extends the framework to include gravity and acceleration, describing how massive objects warp the very fabric of space and time around them. Together, they form one of the most thoroughly tested and carefully confirmed frameworks in all of science, a description of the universe that has passed every experimental challenge it has faced for more than a century. Tonight, we will move through both theories, gently and in detail, from the life of the man who developed them to the black holes and gravitational waves they predict. Let your eyes close if they are ready. The journey begins. Albert Einstein was born on March 14th, 1879, in the city of Ulm, in what was then the Kingdom of Württemberg in the German Empire. He was the first child of Hermann and Pauline Einstein, a middle-class Jewish family. There is a persistent story, repeated so often that it has taken on the quality of established fact, that Einstein was a poor student who failed mathematics as a child. This story is false. Einstein excelled at mathematics and physics from an early age. By the time he was 12, he had taught himself algebra and Euclidean geometry over a single summer. By 15, he had worked his way through differential and integral calculus on his own. The misconception may have arisen partly because he did struggle, not with the subjects themselves, but with the rigid, authoritarian style of education prevalent in German schools of his era, which rewarded rote memorization over creative thinking and did not suit the way his mind worked. After finishing his secondary education in Switzerland, Einstein enrolled at the Swiss Federal Polytechnic in Zurich, where he studied to become a physics and mathematics teacher. He graduated in 1900, but struggled to find an academic position. Partly, it appears, because his independent attitude had not endeared him to his professors, who declined to write him recommendations. After several years of searching, he obtained a position as a technical expert, third class, at the Swiss Federal Patent Office in Bern in 1902. He evaluated patent applications, assessed whether they were technically sound, whether they described novel inventions. The work was methodical and sometimes repetitive, but it suited him in an important way. It left his mind free. The patent office years were, it turned out, among the most productive in the history of physics. In 1905, while still working as a patent examiner, Einstein published 4 papers in the German physics journal Annalen der Physik. Each of them, individually, would have been considered a significant contribution to physics. Together, they transformed the discipline so completely that 1905 is now called Einstein's Annus Mirabilis, his miracle year. The first paper explained the photoelectric effect, the observation that light striking a metal surface can eject electrons, but only if the light has a sufficiently high frequency, regardless of its intensity. Einstein proposed that light consists of discrete packets of energy, what we now call photons, rather than being a continuous wave. This was a revolutionary idea, and it is for this work, not for relativity, that Einstein received the Nobel Prize in Physics in 1921. Relativity was still considered too controversial by the Nobel Committee at the time. The second paper provided theoretical evidence for the existence of atoms, still debated at the time, through an explanation of Brownian motion, the random jiggling of small particles suspended in a fluid. The third paper introduced special relativity. The fourth showed that mass and energy are equivalent, introducing what would eventually be written as equals mc squared. The tools Einstein used to develop these ideas were not primarily laboratory instruments. He was a theoretical physicist, and his primary instruments were thought experiments, imagined scenarios constructed and examined with careful logic. His most famous thought experiment, which he said began forming in his mind around the age of 16, involved imagining what it would look like to ride alongside a beam of light. If you could keep pace with the light, what would you see? A frozen electromagnetic wave suspended in space. Maxwell's equations said this should be impossible, and Einstein took that impossibility seriously, following it patiently until it led him to special relativity. Einstein's personal life during the burn years was relatively quiet. He lived simply, thought deeply, and spent evenings discussing physics with a small group of friends who called themselves the Olympia Academy. He married Mileva Maric, a physicist he had met at the Polytechnic in 1903. Their intellectual partnership was genuine, though the precise extent of her contribution to his early work has been debated by historians. After 1905, Einstein's scientific reputation grew rapidly, and he eventually obtained the academic positions that had eluded him earlier. In 1933, as the Nazi Party rose to power in Germany, Einstein, who was Jewish and a pacifist, was in the United States for a visiting professorship. He did not return to Germany. He settled at the newly founded Institute for Advanced Study in Princeton, New Jersey, where he would work for the rest of his life. His later decades were devoted largely to an attempt to develop a unified field theory, a single mathematical framework that would reconcile general relativity with electromagnetism, bringing together the forces of nature under one description. He worked at this problem persistently and without success for 30 years. Quantum mechanics, which was transforming the rest of physics during this period, he viewed with skepticism, famously asserting that God does not play dice, by which he meant that the fundamental randomness at the heart of quantum theory suggested to him that the theory was incomplete rather than fundamentally correct. Einstein died on April 18, 1955, in Princeton, from the rupture of an aortic aneurysm. He had been offered surgery and declined, reportedly saying that he had done his share and it was time to go. He was 76 years old. His death was front-page news around the world. His brain was preserved, without his family's permission, by the pathologist who performed the autopsy, and studied by researchers for decades in search of anatomical features that might explain his intellectual abilities. Nothing definitive was found. He was, beneath the legend, a person, methodical, imaginative, sometimes difficult, capable of great warmth and occasional self-absorption. A person who sat in a quiet office in Bern, evaluating patent applications, and, in his spare time, thought carefully about what it would mean if the speed of light were truly the same for everyone, and followed that thought all the way to a new description of the universe. For more than 2 centuries, following the publication of Isaac Newton's Principia Mathematica in 1687, Newtonian mechanics and Newtonian gravity stood as the definitive description of the physical world. Newton's laws of motion explained how objects accelerate under forces. His law of universal gravitation explained how every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. Together, these principles allowed physicists and astronomers to calculate the motions of planets, predict the return of comets, explain the tides, and describe the behavior of objects from the microscopic to the astronomical with extraordinary accuracy. Underlying this entire framework were 2 assumptions so fundamental that they were rarely stated explicitly because they seemed obviously true. The first was the assumption of absolute space, the idea that there exists a fixed, immovable reference frame against which all motion can be measured. Newton imagined space as a vast, empty container existing independently of any matter within it, providing an absolute backdrop against which the word stationary had a definite meaning. The second was the assumption of absolute time, the idea that time flows at the same rate everywhere in the universe for all observers, regardless of their motion or position. A second here is the same as a second there, and the same as a second anywhere. Time was universal, uniform, and independent of everything that happened within it. Into this well-ordered framework came James Clerk Maxwell's theory of electromagnetism, published between 1861 and 1865. Maxwell unified electricity, magnetism, and optics into a single mathematical description, one of the great achievements of 19th century physics. His equations predicted that electromagnetic waves, including light, travel through space at a specific, fixed speed, denoted CE, which works out to approximately 300,000 kilometers per second. This was a deeply satisfying result, but it immediately raised a question that proved surprisingly difficult to answer. Fixed at 300,000 kilometers per second, relative to what? In Newtonian mechanics, speeds are always relative. The speed of a ball thrown from a moving train is the speed of the ball relative to the train, plus the speed of the train relative to the ground. It seemed natural to assume that light would behave similarly, that its speed should be measured relative to some medium through which it traveled. Just as sound travels through air, and the speed of sound is measured relative to the air, it was assumed that light must travel through some medium as well. This medium was called the luminiferous ether, a hypothetical substance filling all of space, providing the reference frame relative to which the speed of light was fixed. If the ether existed, then as Earth moved through it during its orbit around the Sun, the speed of light measured in the direction of Earth's motion should differ slightly from the speed measured perpendicular to that motion, just as the apparent speed of the wind is different depending on whether you are walking into it or across it. In 1887, Albert Michelson and Edward Morley designed an exquisitely sensitive experiment to detect this difference. Using a device called an interferometer that could measure tiny differences in the travel time of light beams sent in different directions, they searched for the expected variation in light speed due to Earth's motion through the ether. They found nothing. The speed of light was the same in every direction, regardless of Earth's motion. The result was deeply puzzling. Physicists proposed various explanations. Perhaps the ether was dragged along by Earth. Perhaps moving objects physically contracted in the direction of motion. But none of these explanations was entirely satisfactory. The puzzle sat in the foundations of physics, unresolved. There was another problem that troubled Einstein specifically. Maxwell's equations describe the induction of an electric current when a magnet moves near a conductor, but the mathematical description was different depending on whether you said the magnet was moving or the conductor was moving, even though the relative motion between the two was identical in both cases, and the physical result was the same current. Einstein found this asymmetry aesthetically unacceptable. The laws of physics should not depend on an arbitrary choice of which object you describe as moving. Hendrik Lorentz, a Dutch physicist, had derived the mathematical transformations, now called the Lorentz transformations, that correctly described how space and time coordinates changed between reference frames moving relative to each other. These transformations, it turned out, were the right equations. But Lorentz interpreted them as describing real, physical distortions caused by motion through the ether, length contraction as a physical squeezing of matter by the ether wind, time dilation as a physical slowing of clocks due to their motion. He had the mathematics, but lacked the deeper physical interpretation. Einstein's insight was to reverse the approach entirely. Rather than trying to explain the constant speed of light as a puzzling result that needed explaining away, he took it as a starting postulate, a foundational fact about the universe. And rather than trying to preserve absolute space and absolute time, he was willing to let them go. He followed the logic of the constant speed of light wherever it led, without flinching at the strange conclusions it produced. What followed from that willingness was special relativity. Special relativity is built on two postulates, two foundational statements that Einstein took as the starting points for everything that followed. The first postulate says that the laws of physics are the same for all observers who are moving at constant velocity relative to each other. There is no experiment you can perform inside a smoothly moving vehicle, a train, a ship, a spacecraft moving without acceleration, that will tell you whether you are moving or standing still. All constant velocity motion is relative. There is no absolute rest. The second postulate says that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. If you are standing still and measure the speed of a beam of light, you get approximately 300,000 kilometers per second. If you are moving toward the light source at half the speed of light and measure the same beam, you still get approximately 300,000 kilometers per second. Not 300,000 plus your speed, not 300,000 minus your speed, exactly the same number. These two postulates seem simple enough, but when you follow their logical implications with care, they lead to conclusions that are genuinely surprising. Conclusions that overturn the intuitions about time and space that centuries of everyday experience have built into human thinking. The first surprise is what physicists call the relativity of simultaneity. Imagine two lightning bolts striking the front and back of a moving train at exactly the same moment, as judged by an observer standing on the platform beside the track. The platform observer, standing midway between the two strike points, receives the light from both strikes at the same time and correctly concludes they were simultaneous. But an observer sitting in the middle of the moving train receives the light from the front strike before the light from the rear strike, because the train is moving toward the front and away from the rear. Since the speed of light is the same for both observers, the train observer correctly concludes that the front strike happened first. Two observers, two reference frames, two different answers to the question of whether the lightning bolts struck simultaneously. Neither observer is wrong. Simultaneity is not absolute. The second consequence is time dilation. Consider a clock that keeps time by bouncing a light pulse between two mirrors, one at the floor and one at the ceiling. For an observer standing still beside the clock, the light travels straight up and straight down. For an observer watching the clock move sideways past them at high speed, the light travels a longer diagonal path, up and forward, then down and forward, tracing a zigzag. Since both observers measure the same speed of light, and since the diagonal path is longer than the vertical path, the moving clock must take longer to complete each tick as measured by the stationary observer. Time runs more slowly for the moving clock. The mathematical factor describing this slowing is called the Lorentz factor, denoted by the Greek letter gamma. It equals 1 when the velocity is 0, no time dilation at rest. As velocity increases, the Lorentz factor increases, and the time dilation becomes more pronounced. At 10% of the speed of light, the effect is barely noticeable, clocks running about 0.5% slow. At 90% of the speed of light, the Lorentz factor is approximately 2.29, meaning a moving clock ticks at less than half the rate of a stationary one, and a person traveling at that speed would age at less than half the rate of someone who stayed behind. At 99% of the speed of light, the factor reaches approximately 7.09. At 99.9%, approximately 22.4. The closer to the speed of light, the more dramatically time slows. Alongside time dilation comes length contraction. An object moving at high speed appears shorter in the direction of motion to a stationary observer. At 90% of the speed of light, an object would appear contracted to approximately 44% of its rest length. The object does not feel compressed from its own perspective, from its own reference frame. It is the stationary observer who appears contracted. There is also a third consequence, one that explains why nothing with mass can ever reach the speed of light. As an object moves faster, it becomes increasingly difficult to accelerate further. The energy required to push it faster grows without limit as its speed approaches light speed. To actually reach the speed of light would require an infinite amount of energy, which is simply not available. The speed of light is not simply a very fast speed that objects happen not to reach. It is a geometric feature of the structure of space-time itself, an absolute limit built into the universe's architecture. Running through all of these effects is a unifying concept called the space-time interval. While individual measurements of distance and time differ between observers moving at different velocities, there is a specific combination of space and time measurements that remains the same for all observers. This invariant quantity, the space-time interval, is the geometric heart of special relativity. It is what is truly absolute in a theory that is not, despite its name, about everything being relative. Of all the things to emerge from Einstein's work in 1905, the equation E equals mc squared is the most widely recognized, perhaps the most widely recognized equation in the history of science. It appears on posters and coffee mugs and t-shirts. It is quoted in films and novels and political speeches. Most people have seen it. Fewer people have a clear sense of what it actually says. And fewer still realize that Einstein did not write it in that compact and elegant form in his original paper. The familiar notation developed gradually over time as physicists refined the expression of the idea. What the equation says at its core is that mass and energy are not two separate things, but two manifestations of the same physical quantity. Energy can be converted to mass, and mass can be converted to energy. The letter E represents energy, M represents mass, and C represents the speed of light. The speed of light is approximately 300,000 kilometers per second. Squared, it becomes approximately 90 quadrillion, 90 million billion, meters squared per second squared. This is a very large number, and it appears as a conversion factor in the equation. Even a very small mass, when multiplied by c squared, corresponds to an enormous amount of energy. Consider a single paperclip with a mass of approximately 1 gram. Multiplied by c squared, this tiny mass is equivalent to approximately 90 trillion joules of energy, enough to power a city of roughly 1 million people for an entire day. Mass, it turns out, is extraordinarily concentrated energy. In nuclear reactions, both fission, in which heavy atomic nuclei split apart, and fusion, in which light nuclei join together, the products of the reaction have slightly less mass than the starting materials. This small deficit in mass is converted to energy via E equals mc squared. The amounts of mass involved are tiny, a fraction of a percent of the total. But because c squared is so large, even these tiny mass deficits correspond to enormous energy releases. This is the principle underlying nuclear power plants, nuclear weapons, and the energy output of the Sun and all other stars. The Sun converts approximately 4 million tons of mass to energy every second through nuclear fusion in its core, hydrogen nuclei fusing to form helium, with the mass deficit released as the light and heat that sustains life on Earth. This has been happening for approximately 4.5 billion years and will continue for another 5 billion or so. The energy that warms every sunny afternoon on Earth is mass, a very small amount of the Sun's mass, that ceased to exist as mass and became light instead. In medicine, E equals mc squared has a practical and life-saving application. Positron emission tomography, PET scanning, uses a radioactive tracer that emits positrons, the antimatter counterparts of electrons. When a positron meets an electron in the patient's body, both particles are annihilated. Their mass is converted entirely to energy in the form of 2 gamma rays flying in opposite directions. The scanner detects these gamma ray pairs and uses their directions to reconstruct a 3-dimensional image of metabolic activity inside the body. The diagnosis of cancer, neurological conditions, and heart disease all benefit from this technology that depends directly on the most famous equation in physics. There are subtler applications of E equals mc squared as well, ones that touch everyday objects in less obvious ways. Most of the mass of a proton or neutron does not come from the quarks inside it. Quarks themselves have relatively small masses. The majority of the proton's mass comes from the energy of the gluon field, the field that binds the quarks together, which contributes to the proton's mass via E equals mc squared. In a very real sense, most of the mass of everything around you, every table, every wall, every human body, is not the mass of the particles themselves, but the energy of the forces binding those particles. Matter is, in large part, energy in a very stable and concentrated form. Relativistic effects extend into the chemistry of specific materials in ways that are genuinely surprising. The characteristic yellow color of gold, the warm, distinctive hue that has made it aesthetically prized across human cultures for millennia, is partly a consequence of special relativity. Electrons in gold atoms move at velocities that are significant fractions of the speed of light. At these speeds, relativistic effects contract the electron orbits, shifting the energies of specific electron transitions into the visible light range. This shifts the wavelengths of light that gold absorbs, causing it to reflect yellow and orange light that other metals do not. Without relativistic effects, gold would be silvery white, like most other metals. Mercury's famous liquid state at room temperature, unusual for a metal, is also partly attributable to relativistic contraction of its electron configuration, which weakens the metallic bonds that hold mercury atoms together. In 1908, 3 years after Einstein published Special Relativity, a mathematician named Hermann Minkowski gave a lecture that began with one of the most memorable sentences in the history of physics. Minkowski had been Einstein's professor of mathematics at the Zurich Polytechnic, and by his own account, Einstein had not impressed him particularly as a student, being something of an irregular attendee. But when Minkowski studied Einstein's 1905 paper carefully, he recognized something in it that Einstein himself had not fully articulated, a beautiful geometric structure lying just beneath the surface of the equations. His lecture began, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." The union he was describing was space-time, the four-dimensional continuum that combines the three familiar dimensions of space with the dimension of time into a single unified structure. Einstein's initial reaction to Minkowski's formulation was reportedly one of mild annoyance. He felt that what was essentially a piece of physics was being buried under excessive mathematics. Over time, however, and especially as he began developing general relativity, Einstein came to regard Minkowski's geometric interpretation as not merely a useful reformulation, but as the deep truth underlying the theory. It was Minkowski's spacetime that pointed the way forward. What does it mean to say that space and time form a four-dimensional continuum? It means that every event in the universe, every point in space at a specific moment in time, is a single point in four-dimensional spacetime, specified by four coordinates, three spatial coordinates and one time coordinate. The motion of an object through space over time traces a path through this four-dimensional structure, a path called a world line. The entire history of an object, from its beginning to its end, is a curve in space-time. The relationship between the space and time dimensions in space-time is not quite what everyday intuition might suggest. They are not simply four equal dimensions. The time dimension enters the equations with a minus sign, giving space-time a geometry that is fundamentally different from ordinary Euclidean four-dimensional space. This unusual geometry is captured in the space-time interval, the invariant quantity that all observers agree on regardless of their relative motion. While different observers may measure different distances and different time separations between the same two events, they all calculate the same space-time interval between those events. There is a concept in special relativity called proper time, the time measured by a clock that is carried along a specific path through space-time. Proper time is an invariant. It is the actual elapsed time on that particular clock, and all observers agree on its value. Different paths through space-time can have different proper times between the same two events, and this is precisely what produces the time dilation effects described in the previous section, and the twin paradox described in the next. Every object in the universe, whether it is moving or sitting still, is traveling through space-time. An object at rest in space is still moving through time. Its world line extends into the future. An object moving through space is redirecting some of its motion from the time direction into the space directions. In a certain sense, everything moves through space-time at the same speed, the speed of light, trading between spatial motion and temporal motion. A photon of light, which moves at the speed of light through space, experiences no motion through time at all. A person sitting perfectly still experiences all their space-time motion in the time direction. They are not moving through space, but they are traveling through time at the rate of 1 second per second. The photon situation is particularly striking when considered carefully. Light travels at the speed of light, which means, from special relativity, that its clock runs at 0 rate. From a photon's perspective, to the extent that a photon can be said to have a perspective, it is emitted and absorbed in the same instant. The journey from the surface of the Sun to the surface of Earth, which takes approximately 8.3 minutes in our experience, takes no time at all from the photon's perspective. The journey across the Milky Way, which takes 100,000 years in our experience, takes no time for the photon. A photon emitted at the Big Bang and absorbed by a telescope on Earth today has experienced no time at all in its entire existence. Its creation and its absorption are, from its frame of reference, simultaneous events. The philosophical implications of the four-dimensional block universe are profound. In ordinary thinking, the past is fixed, the future is open, and the present is a moving boundary between them, a universal now sweeping through time. But in the four-dimensional space-time of relativity, there is no universal now. Different observers disagree about which events are simultaneous, which means there is no single present moment that is shared by all observers. The past, present, and future of different observers overlap in complex ways. The four-dimensional block, all events everywhere, from the beginning to the end of time, simply exists as a static geometric structure, and what we experience as the flow of time is our particular path through it. Among the many thought experiments that illuminate the consequences of special relativity, the twin paradox is probably the most famous and the most useful for making the abstract feel concrete. It asks a simple question. Suppose one member of a pair of twins boards a spacecraft and travels at high speed to a distant star, then turns around and returns to Earth. Upon landing, the traveling twin discovers that their sibling has aged considerably more than they have. The traveling twin has experienced less time than the twin who stayed home. This is the time dilation of special relativity made personal. But it immediately seems to raise a problem. If all motion is relative, if we can equally well say that the spacecraft moved away from Earth, or that Earth moved away from the spacecraft, then why is the situation not symmetric? Why does the traveling twin age less rather than both twins aging equally? The resolution lies in the distinction between constant velocity motion and accelerating motion. Special relativity tells us that the laws of physics are the same for all observers moving at constant velocity. But the traveling twin does not move at constant velocity throughout the journey. They must decelerate to stop at the distant star, accelerate again to turn around, decelerate to stop at Earth, and so on. This acceleration breaks the symmetry between the two twins. The traveling twin follows a curved path through space-time, one that, despite covering enormous spatial distances, actually spans less proper time than the straight space-time path of the twin who remained on Earth. The geometry of space-time is such that the longest proper time between two events corresponds to the straightest path through space-time, the path with no acceleration. The time dilation predicted by special relativity is not a hypothetical possibility waiting to be tested. It is a measured, confirmed, and practically important fact. One of the most direct demonstrations came in 1971, when two physicists, Joseph Haffel and Richard Keating, carried 4 cesium atomic clocks aboard commercial airliners and flew them around the world, first eastward and then westward. When the traveling clocks were compared to reference clocks that had remained on the ground, they showed exactly the time differences predicted by relativity, accounting for both the time dilation due to the aircraft's speed relative to the ground and the gravitational time dilation due to the aircraft's altitude. The more consequential everyday application of relativistic time dilation is one that billions of people depend on without knowing it. The Global Positioning System, GPS, relies on a constellation of satellites orbiting Earth at an altitude of approximately 20,000 kilometers. Each satellite carries an extremely precise atomic clock, and your GPS receiver determines your position by comparing the timing signals it receives from multiple satellites simultaneously. For this to work, the satellite clocks must stay synchronized with clocks on the ground to within a few nanoseconds. But the satellite clocks are subject to 2 competing relativistic effects. The satellites move at approximately 14,000 kilometers per hour, fast enough that special relativistic time dilation causes their clocks to run slow by approximately 7 microseconds per day relative to ground clocks. At the same time, the satellites are at a higher altitude where Earth's gravitational field is weaker, and general relativistic time dilation, which we will explore in detail later, causes their clocks to run fast by approximately 46 microseconds per day. The net effect is that satellite clocks run fast by about 38 microseconds per day. If this were not corrected for, the accumulated error would cause GPS positioning to drift by approximately 10 kilometers per day, rendering the system useless for navigation within hours of operation. The relativistic corrections are built into the GPS system's design and applied continuously. Every time someone navigates to an unfamiliar address, relativity is working silently in the background. The time dilation of special relativity is also directly confirmed by an everyday atmospheric phenomenon. Cosmic rays, high-energy particles arriving from space, collide with atoms in the upper atmosphere and produce secondary particles called muons. Muons are unstable. At rest, they decay with a half-life of approximately 2.2 microseconds. Created at altitudes of approximately 15 kilometers, they should, by ordinary calculation, decay long before reaching the ground. Traveling at close to the speed of light, they cover only about 600 meters in 2.2 microseconds before half of them have decayed. Yet, detectors at sea level register large numbers of muons. The explanation is time dilation. Traveling at approximately 98% of the speed of light, their internal clocks run at a fraction of the rate of a stationary clock. From our perspective, their lifetimes are extended by a factor of approximately 5, enough for them to reach the ground before decaying. Moons reaching sea level are not a curiosity. They are a daily, measurable confirmation that time dilation is real. Even at the much more modest speeds and altitude differences of everyday human life, relativistic effects are present. A person living at high altitude ages very slightly faster than someone at sea level because gravitational time dilation runs clocks faster at higher altitudes. The effect is immeasurably small in any human lifetime, amounting to microseconds over decades. But it is real, and it is the same physics that makes GPS work. Special relativity, for all its power, has a limitation built into its name. It is special, meaning it applies to a special case. It describes physics in inertial frames, reference frames moving at constant velocity. It handles time dilation and length contraction and E equals mc squared with elegance and precision. But it says nothing about gravity. And gravity is one of the most fundamental aspects of physical experience. The force that holds planets in orbit, keeps us on the ground, and shapes the large-scale structure of the universe. Einstein began working on how to extend his theory to include gravity almost immediately after publishing Special Relativity in 1905. The process took a decade, 10 years of increasingly sophisticated mathematical work, false starts, near misses, and moments of genuine insight. The key that unlocked the door was a principle so simple and so deep that Einstein later described the moment of recognizing it as the happiest thought of his life. The principle is called the equivalence principle. It states that the effects of gravity and the effects of acceleration are, locally and in a small enough region, completely indistinguishable. Consider a simple thought experiment. You are inside a sealed box with no windows, no way of seeing the outside world. The box is sitting on the surface of Earth. You feel a force pulling you toward the floor. You weigh objects and find they have their normal terrestrial weights. Everything behaves exactly as you expect on Earth. Now imagine the same sealed box, far from any gravitating body, being accelerated upward by a rocket engine at exactly 9.8 meters per second squared. The same acceleration as Earth's gravitational pull at the surface. You feel a force pulling you toward what is now the floor of the accelerating box. You weigh objects and find they have the same weights as on Earth. Everything behaves in exactly the same way. No experiment you can perform inside the box will distinguish between these two situations. Gravity and acceleration are locally equivalent. This seemingly simple observation has profound consequences. Consider what acceleration does to time. An observer at the front of an accelerating rocket ages slightly faster than an observer at the back. This follows from the Doppler-like effect that the front of the rocket is accelerating away from signals sent from the back, causing those signals to arrive at a lower frequency, which translates to a slower rate of time passing at the back. If acceleration affects time in this way, and if gravity is locally equivalent to acceleration, then gravity must also affect time. Clocks in stronger gravitational fields must run slower. Time must pass more slowly, deep in a gravitational well, than high above it. This is gravitational time dilation. Now consider what the equivalence principle implies for light. Imagine a beam of light entering through a small hole in the wall of the accelerating box, traveling horizontally across the box. By the time the light reaches the opposite wall, the box has accelerated upward, so the point where the light hits the wall is slightly lower than where it entered. An observer inside the box sees the light curve downward, but by the equivalence principle, an observer in a gravitational field must see the same thing. Gravity must bend light. Both of these predictions, gravitational time dilation and the bending of light, follow directly from the equivalence principle without any need for detailed equations. But Einstein wanted more than these qualitative insights. He wanted a complete mathematical theory of gravity that reduced to Newtonian gravity in the appropriate limit and could make precise quantitative predictions. The development of that theory required several more years and the help of his friend, the mathematician Marcel Grossmann, who guided him through the mathematics of curved spaces developed by Bernhard Riemann in the mid-19th century. The central insight of general relativity is that gravity is not a force at all, at least not in the way Newton understood it. Gravity is the curvature of space-time caused by the presence of mass and energy. A massive object like the Sun does not reach across space and pull the Earth toward it with some mysterious action at a distance force. Instead, the Sun's mass causes the four-dimensional geometry of the space-time around it to curve. Earth moves through this curved space-time along the straightest path available to it, called a geodesic. And that geodesic happens to be what we observe as Earth's elliptical orbit. Earth is not being pulled toward the Sun. It is following the natural geometry of the space-time the Sun has curved around itself. The rubber sheet analogy captures some of this intuition. Place a heavy ball on a stretched rubber sheet. It sinks, creating a curved depression in the sheet. Place a smaller ball nearby, and it rolls towards the large ball, following the curve of the sheet. Replace the rubber sheet with four-dimensional space-time. Replace the balls with masses, and you have a rough picture of general relativity. The analogy is imperfect. The rubber sheet requires gravity to work in the first place. It shows only the spatial curvature rather than the full space-time curvature, and it lives in 3 dimensions rather than 4. But it captures the essential idea that mass shapes the geometry of its surroundings and other masses move in response to that geometry. The mathematical heart of general relativity is a set of equations that Einstein arrived at in November 1915 after years of searching. These are the Einstein field equations, 10 interrelated differential equations that relate the geometry of space-time to the distribution of matter and energy within it. They are among the most beautiful and most complex equations in all of physics, and understanding what they say, even without working through the mathematics, reveals something profound about how Einstein conceived of the universe. The equations have a left side and a right side. The left side describes the curvature of space-time. how the four-dimensional geometry of the universe bends and curves at every point. The right side describes the content of space-time, the distribution of matter, energy, pressure, momentum, and stress at every point. The equations say, in essence, that these two things are equal, that the curvature of space-time at any point is determined by the matter and energy at that point, and conversely, that the distribution of matter and energy is shaped by the curvature of space-time. Einstein himself summarized the content of his equations in an informal phrase that has become one of the most memorable descriptions in physics. Space-time tells matter how to move, and matter tells space-time how to curve. The equations are nonlinear, which means that solutions cannot simply be combined or added together, and that small changes in the matter distribution can produce disproportionate changes in the space-time geometry. This nonlinearity makes the equations extraordinarily difficult to solve exactly. In the more than a century since Einstein published them, only a handful of exact analytical solutions have been found. Solutions describing idealized situations, simple enough to yield to the mathematics. The first and most important exact solution was derived not by Einstein, but by Karl Schwarzschild, a German physicist and astronomer serving as an artillery officer on the Russian front during the First World War. In December 1915, just weeks after Einstein published the field equations, Schwarzschild solved them for the case of a perfectly spherical, non-rotating mass in otherwise empty space. He sent his solution to Einstein in January 1916 with a note explaining that the war had been kind enough to allow him time for this calculation. Einstein was moved. Schwarzschild died in May 1916 from a skin disease contracted at the front, having never returned home. The Schwarzschild solution describes the geometry of space-time in the empty space around any spherical mass, a star, a planet, or anything else. It works beautifully, but it also contains a curious feature. There is a specific radius, now called the Schwarzschild radius, at which the equations become singular. For any mass, this radius is given by a simple formula: 2 times Newton's gravitational constant times the mass, divided by the square of the speed of light. For Earth, this works out to approximately 9 millimeters, roughly the size of a marble. For the Sun, approximately 3 kilometers. For a typical stellar remnant of 10 solar masses, approximately 30 kilometers. The physical meaning of the Schwarzschild radius is this: if any mass were compressed to within its own Schwarzschild radius, the escape velocity from its surface would equal the speed of light. Nothing, not even light, could escape. The region inside the Schwarzschild radius would be permanently cut off from the rest of the universe. This is a black hole, and the Schwarzschild radius defines the size of its event horizon, the boundary beyond which no information can return. Einstein himself was skeptical that black holes were real physical objects rather than mathematical artifacts of the equations. This skepticism persisted for decades in much of the physics community. Over time, however, observations accumulated confirming that black holes not only exist, but are among the most common and important structures in the universe. The field equations also contain a term that Einstein added in 1917, the cosmological constant, represented by the Greek letter lambda. Einstein included this term to produce a static, non-expanding universe, which was the prevailing assumption at the time. The cosmological constant acted as a kind of repulsive force that counteracted gravity on the largest scales, keeping the universe from collapsing under its own gravitational pull. When Edwin Hubble's observations in 1929 showed that distant galaxies were receding from us, that the universe was expanding, Einstein reportedly called the cosmological constant his greatest blunder and removed it from his equations. The irony is that modern cosmology has revived the cosmological constant as the mathematical description of dark energy, the mysterious component driving the accelerating expansion of the universe. What Einstein introduced as an ad hoc correction and discarded as a mistake turns out to describe something real. The no-hair theorem is another elegant result that follows from the mathematics of general relativity. It states that a black hole in equilibrium is completely characterized by just three parameters: its mass, its electric charge, and its angular momentum. All the detailed information about the matter that formed the black hole, its chemical composition, its temperature, its internal structure, is lost. The black hole retains only these three numbers, and two black holes with the same mass, charge, and spin are physically identical, regardless of how they were formed. A theory in physics is only as good as the experiments that test it. Einstein's general relativity made predictions that were, when it was published in 1915, far beyond the capacity of existing technology to confirm. Some of its most important predictions took decades to test. Others took a full century. The story of how general relativity has been tested and how it has passed every test is one of the most sustained and carefully conducted programs of experimental verification in the history of science. The first confirmation came almost immediately, and it concerned a problem that had been puzzling astronomers for decades. The planet Mercury orbits close to the Sun, where the Sun's gravitational field is strongest. Over many years of careful observation, astronomers had measured that Mercury's orbit was not a perfectly fixed ellipse. Instead, the ellipse itself slowly rotated, a phenomenon called precession of the perihelion, where the perihelion is the point in the orbit closest to the Sun. Most of this precession was accounted for by the gravitational pull of the other planets, but approximately 43 arcseconds of precession per century remained unexplained by Newtonian gravity. 43 arcseconds per century is an extraordinarily small angle, about the width of a human hair seen from a distance of more than 200 meters. But it was real, it was measured, and Newton's theory could not explain it. When Einstein applied his field equations to the problem of Mercury's orbit, the unexplained 43 arcseconds emerged naturally from the calculation. The curvature of space-time near the Sun, as described by general relativity, caused exactly the right amount of additional precession. Einstein reportedly was so excited when the numbers came out correctly that he experienced heart palpitations. It was the first confirmation that his theory described something real about the universe. The second great confirmation came in 1919, and it made Einstein world famous in a way that the Mercury calculation, appreciated only by specialists, never could. General relativity predicted that light passing near a massive object would be bent by the curvature of space-time, and that the degree of bending would be twice what Newtonian gravity predicted for light treated as a particle with mass. During a solar eclipse, when the moon blocks the sun's bright disk, it becomes possible to observe stars whose light passes close to the sun. By comparing the apparent positions of these stars during the eclipse with their known positions when the sun is elsewhere, the bending of their light can be measured. Arthur Eddington, a British astronomer who had followed Einstein's work carefully, organized 2 expeditions to observe the solar eclipse of May 29, 1919. One to the island of Principe off the coast of West Africa, and one to Sobral in northern Brazil. Working under difficult conditions, cloudy weather threatened to ruin the Principe observations. They photographed the stars near the eclipsed sun and compared the results to photographic plates taken months earlier. The apparent positions of the stars were shifted by approximately 1.75 arc-seconds, exactly the amount predicted by general relativity, and twice the Newtonian prediction. The results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London in November 1919, and newspapers around the world reported the news the following day. Einstein became, overnight, a global scientific celebrity. In the decades that followed, increasingly precise tests confirmed general relativity's predictions with growing accuracy. In 1959, Robert Pound and Glenn Rebka confirmed gravitational redshift, the slowing of light's frequency as it climbs out of a gravitational field. By measuring the tiny difference in the frequency of gamma rays emitted at the bottom and detected at the top of a tower at Harvard University, a height difference of only 22.6 meters. The measured redshift matched the prediction of general relativity. In the 1960s and 1970s, the Shapiro delay, the extra time taken by radar signals passing close to the sun, was measured and confirmed. In 2004 and 2005, the Gravity Probe B satellite measured frame dragging, the dragging of space-time by Earth's rotation, using gyroscopes in orbit, confirming the predicted effect to approximately 0.3% precision. The equivalence principle, the cornerstone of general relativity, has been tested to 1 part in 10 to the 15th power, making it one of the most precisely verified principles in all of science. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, 2 neutron stars orbiting each other at close range. Because neutron stars are extraordinarily dense, their orbital velocity is high, and the curvature of space-time around them is significant. General relativity predicted that the system would slowly lose energy by radiating gravitational waves, space-time ripples, causing the 2 stars to spiral slowly toward each other. Hulse and Taylor monitored the system for years, measuring the decay of the orbital period with extraordinary precision. The observed rate of orbital decay matched the prediction of general relativity with remarkable accuracy. This was the first indirect evidence that gravitational waves were real, a confirmation so definitive that Hulse and Taylor received the Nobel Prize in Physics in 1993. The direct detection of gravitational waves came in 2015, 100 years after Einstein published General Relativity. When the LIGO collaboration announced the detection of a signal from the merger of 2 black holes approximately 1.3 billion light-years away. This detection, and the many that have followed, have confirmed that gravitational waves travel at the speed of light, that black holes exist with the properties general relativity predicts, and that the strong field behavior of gravity matches Einstein's equations precisely. More than a century after it was written, general relativity continues to pass every experimental test placed before it. A black hole forms when enough mass is concentrated in a small enough region that the escape velocity, the speed required to leave the gravitational field, exceeds the speed of light. Since the speed of light is the cosmic speed limit, nothing can escape. The boundary of this region is called the event horizon. It is not a physical surface. There is no wall, no barrier, no material boundary at the event horizon. It is a geometric feature of space-time, the surface at which the future light cone of any event inside it is directed entirely inward, so that every possible future path from inside the horizon leads deeper into the black hole rather than out of it. Approaching a black hole from outside, the effects of its extreme space-time curvature become progressively more pronounced. Clocks near the event horizon run dramatically slower than clocks far away, an extreme form of the gravitational time dilation described by general relativity. From the perspective of a distant observer watching someone fall into a black hole, the infalling person appears to slow down as they approach the horizon, their light becoming increasingly redshifted and dim, their image seeming to freeze just outside the event horizon as time appears to stop. They never appear to cross the horizon. They are eternally suspended just outside it in the distant observer's view. From the perspective of the infalling person, the experience is quite different. If the black hole is large enough, with a mass of millions or billions of solar masses, the tidal forces at the event horizon are mild, and the crossing is uneventful. There is no sudden sensation, no physical barrier, no obvious signal that the horizon has been crossed. Only afterward, inside the horizon, does the traveler realize that every possible path forward leads toward the singularity at the center. They cannot send signals back to the outside universe. Those signals would need to travel faster than light to escape, which is impossible. They are inside, and there is no way out. Closer to the center, tidal forces become increasingly severe. The difference in gravitational pull between the head and the feet of any extended object stretches that object radially while compressing it laterally, a process colloquially known as spaghettification. For small black holes with masses comparable to a few times the Sun, these tidal forces are already extreme at the event horizon. For supermassive black holes with billions of solar masses, the tidal forces at the event horizon are actually relatively gentle, and spaghettification only becomes severe much closer to the singularity. At the center of a black hole, the Schwarzschild solution to Einstein's field equations predicts a singularity, a point where the density becomes mathematically infinite. Most physicists interpret this not as a real physical feature of black holes, but as a signal that general relativity itself breaks down at these extreme conditions, that a quantum theory of gravity, which does not yet exist, is needed to describe what actually happens at the center of a black hole. The singularity is where the known laws of physics reach their limits. In 1974, Stephen Hawking applied quantum mechanical reasoning to the region just outside the event horizon and found a surprising result. The vacuum of space near the horizon is not truly empty. Quantum fluctuations continuously produce pairs of virtual particles. Near the event horizon, these pairs can be separated by the intense gravitational field, one particle falling in while the other escapes. The escaping particle carries energy away from the black hole, causing it to slowly lose mass. Over immensely long timescales, far longer than the current age of the universe for any stellar or supermassive black hole. This Hawking radiation would cause the black hole to evaporate entirely. This prediction leads directly to the information paradox. If the radiation is purely thermal and carries no information about what fell in, then the information encoded in the infalling matter is permanently destroyed, violating a fundamental principle of quantum mechanics. This paradox remains one of the deepest unresolved problems in theoretical physics. The first direct image of a black hole was released on April 10, 2019, by the Event Horizon Telescope collaboration. The target was the supermassive black hole at the center of the galaxy, Messier 87, designated M87 star, with a mass of approximately 6.5 billion solar masses, located approximately 55 million light-years away. The image showed a bright, asymmetric ring of emission surrounding a dark central shadow, the photon ring and shadow predicted by general relativity. The size of the shadow was consistent with the theory's predictions. In May 2022, the same collaboration released the first image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, with a mass of approximately 4 million solar masses, located about 26,000 light-years from Earth. In 1916, 1 year after publishing General Relativity, Einstein predicted the existence of gravitational waves, ripples in the fabric of space-time itself, propagating outward from their source at the speed of light. He derived this prediction from his field equations and showed that any accelerating mass should produce these waves. He also calculated, however, that the waves produced by any physically realistic source would be so unimaginably tiny that he doubted they could ever be detected. The universe, he seemed to believe, had provided a prediction that would remain forever beyond the reach of experiment. He was wrong. A century later, on September 14, 2015, two detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded a signal that lasted a fraction of a second in their sensitive frequency band. After months of careful analysis, the LIGO collaboration announced the result on February 11, 2016. Gravitational waves had been detected for the first time. Einstein's century-old prediction had been confirmed, and a new era in astronomy had begun. A gravitational wave is a distortion in the geometry of space-time, a stretching and squeezing of space itself that propagates outward from its source like a ripple on a pond. As a gravitational wave passes through a region of space, it alternately stretches distances in one direction while compressing them in the perpendicular direction, then reverses. If a gravitational wave were passing through the room where you are resting right now, the room would be very slightly elongated in one direction and compressed in the other, and then the reverse, dozens of times per second. The effect is real, but its magnitude is almost beyond imagination. The most powerful sources of gravitational waves are compact objects in extreme orbital configurations, particularly merging black holes and merging neutron stars, where the masses involved are enormous and the orbital velocities approach the speed of light. As such, a pair spirals together. The gravitational waves they emit carry energy away from the system, causing the orbit to shrink progressively faster. In the final moments before merger, the frequency and amplitude of the waves increase rapidly in what physicists call a chirp, a rising tone that terminates abruptly at the moment of merger. The two objects become one. The merged remnant rings down like a struck bell, and the gravitational wave signal fades. To detect such signals requires a detector of extraordinary sensitivity. The LIGO observatories, two L-shaped facilities located in Livingston, Louisiana, and Hanford, Washington, each with arms 4 kilometers long, use a technique called laser interferometry. A laser beam is split into two beams that travel along the two perpendicular arms, bounce off mirrors at the ends, and return to recombine. If a gravitational wave passes through, it changes the relative lengths of the two arms by an infinitesimal amount, causing the recombined beams to be very slightly out of phase, producing a detectable change in the light pattern. The sensitivity required is almost incomprehensible. The first detected gravitational wave signal, designated G150914, changed the length of LIGO's 4-kilometer arms by approximately 4 times 10 to the power of -18 meters. This is about 1,000th the diameter of a proton, the particle at the center of an atomic nucleus. Detecting this required not only extraordinary precision, but also extraordinary isolation from vibration, thermal noise, quantum noise in the laser, and countless other sources of interference. The achievement represents one of the most technically demanding experiments in the history of science. The source of GW150914 was identified as the merger of two black holes, one with a mass of approximately 29 times the Sun and the other approximately 36 times the Sun, located roughly 1.3 billion light-years from Earth. The two holes spiraled together and merged in the final fraction of a second of the signal, forming a single black hole of approximately 62 solar masses. The missing 3 solar masses were radiated away as gravitational waves in that instant, an amount of energy equivalent to approximately 3 times the mass of the Sun, converted entirely to gravitational wave energy in less than a second. At the moment of merger, the power output exceeded the combined luminosity of all stars in the observable universe. On August 17, 2017, LIGO and the European Virgo detector jointly detected the merger of 2 neutron stars, the first event of this type. This detection was unique because neutron star mergers produce not only gravitational waves, but also light across the entire electromagnetic spectrum. Within 2 seconds of the gravitational wave signal, gamma-ray observatories detected a burst of gamma rays from the same location. Over the following days and weeks, astronomers around the world observed the fading optical glow of a kilonova, the explosion produced by the merger, in the galaxy NGC 4993, approximately 130 million light-years away. This event confirmed several long-standing predictions simultaneously: that short gamma-ray bursts are produced by neutron star mergers, that gravitational waves and light travel at the same speed, and that the merger of neutron stars produces heavy elements, including gold and platinum, through a process called rapid neutron capture. The Einstein field equations describe not only the behavior of gravity around individual stars and black holes, but also the behavior of the universe as a whole. When Einstein first applied his equations to cosmology, to the universe taken as a single system, he found that the solutions did not describe a static universe. They described a universe that was either expanding or contracting. In 1917, this was an uncomfortable result. The prevailing scientific view at the time was that the universe was eternal, infinite, and essentially unchanging. No one had yet measured the recession of distant galaxies. No one had evidence that the universe was doing anything as dramatic as expanding. Einstein was bothered enough by the non-static solutions to introduce an additional term into his equations: the cosmological constant, represented by the Greek letter lambda. This term acted as a kind of repulsive force on the largest scales, precisely counteracting the attractive pull of gravity and allowing a static universe to exist in the mathematics. It was, in retrospect, an ad hoc modification, a term added not because the physics demanded it, but because Einstein wanted the equations to produce a result he believed was correct. In 1922, the Russian mathematician Alexander Friedmann showed that Einstein's equations, without the cosmological constant, described a family of expanding or contracting universes, solutions that are now called the Friedmann models. Einstein dismissed Friedmann's work as mathematically suspicious, then later conceded it was correct, but insisted the solutions were not physically meaningful. Then in 1929, Edwin Hubble published observations showing that galaxies outside the Milky Way were moving away from us, and that the farther they were, the faster they were receding. The universe was expanding. The Friedmann solutions were not mathematical artifacts. They were the correct description of reality. Einstein reportedly called the cosmological constant his greatest blunder. Running the expansion of the universe backward in time, like a film played in reverse, leads to the conclusion that the universe was once in a state of extraordinary density and temperature, compressed into an unimaginably small volume. This is the Big Bang, the beginning of the universe as described by general relativity. The Penrose-Hawking singularity theorems, derived in the 1960s and 1970s, proved mathematically that under very general conditions, the equations of general relativity require an initial singularity, a beginning of time itself. The Big Bang is not an explosion of matter into pre-existing space. It is the beginning of space and time together, the point before which the concept of before has no meaning within the framework of general relativity. The observable evidence for the Big Bang includes the cosmic microwave background, a faint glow of thermal radiation filling the entire sky, first detected by Arno Penzias and Robert Wilson in 1965. This radiation is the afterglow of the early universe, light that was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for neutral atoms to form and photons to travel freely through space for the first time. The temperature of this background radiation is now approximately 2.725 degrees above absolute zero, with tiny fluctuations of 1 part in 100,000 that carry the imprint of the density variations that eventually grew into galaxies, galaxy clusters, and the large-scale structure of the universe. Gravitational lensing, the bending of light by massive objects predicted by general relativity, has become one of the most powerful tools in modern astronomy. When a massive galaxy or galaxy cluster lies between Earth and a more distant object, the light from the distant object is bent and distorted as it passes through the gravitational field of the intervening mass. This can produce magnified, distorted, or multiple images of the background source. Astronomers use these distortions to map the distribution of mass in the intervening cluster, including the vast amounts of dark matter that emit no light but make their presence known through their gravitational effects. Gravitational lensing has provided some of the most direct evidence for the existence of dark matter and has been used to observe galaxies so distant and faint that they would be invisible without the natural magnification provided by the intervening lens. The accelerating expansion of the universe, discovered in 1998 through observations of distant supernovae, has revived the cosmological constant in a new form. The expansion of the universe is not slowing down under the influence of gravity, as might be expected. It is speeding up. Some form of energy inherent in empty space is driving this acceleration, what cosmologists call dark energy. The cosmological constant provides a precise mathematical description of dark energy, treating it as the energy density of the vacuum itself. In the current best model of the universe, dark energy accounts for approximately 68% of the total energy content, dark matter for approximately 27%, and the ordinary matter of stars, planets, and people for only about 5%. The universe described by general relativity has no center and no edge. Every location in the universe is equivalent to every other location on the largest scales. The cosmological principle. From any galaxy in the universe, all other galaxies appear to be receding, and the farther they are, the faster they seem to recede. This is not because everything is moving away from some central point. It is because space itself is expanding everywhere simultaneously. Every region of space growing larger, carrying galaxies apart like dots on the surface of an inflating balloon. General relativity is one of the most precisely confirmed theories in the history of science. It has passed every experimental test to which it has been subjected for more than a century. It describes the universe from the scale of solar systems to the scale of the observable cosmos with extraordinary accuracy. And yet, there is a sense in which it is an unfinished theory, a magnificent achievement that nevertheless points clearly toward its own incompleteness, and that leaves some of the deepest questions in physics unresolved. The most fundamental limitation of general relativity is its incompatibility with quantum mechanics, the equally successful theory that describes the behavior of matter and energy at the smallest scales. Quantum mechanics governs the behavior of atoms, electrons, photons, and the fundamental particles of which all matter is made. It is the foundation of chemistry, solid-state physics, and the technology of semiconductors and lasers. Like general relativity, it has passed every experimental test ever devised for it. And the two theories are, at a deep mathematical level, inconsistent with each other. General relativity describes gravity as the smooth, continuous curvature of a smooth, continuous space-time. Quantum mechanics describes nature as fundamentally discrete and probabilistic. Particles and fields taking definite values only when measured, existing in superpositions of states until observation forces them into one. When physicists try to apply quantum mechanical principles to the gravitational field to develop what is called quantum gravity, the mathematics produces infinities that cannot be removed by standard techniques. The two theories speak different mathematical languages, and their combination does not make sense with the tools currently available. This incompatibility becomes practically important at the extremes that general relativity itself predicts. Inside a black hole, near the singularity, the curvature of space-time becomes so extreme and the densities so high that quantum mechanical effects on the gravitational field cannot be ignored. General relativity alone cannot describe what happens there. Similarly, in the earliest instance of the Big Bang, when the universe was compressed to densities far beyond those of atomic nuclei, both gravity and quantum mechanics are simultaneously relevant, and neither theory alone is adequate. The singularities that general relativity predicts at the center of black holes and at the beginning of the universe are, most physicists believe, signals that the theory has been pushed beyond its domain of validity. The two leading approaches to a quantum theory of gravity are string theory and loop quantum gravity. String theory proposes that the fundamental constituents of nature are not point-like particles, but tiny one-dimensional objects called strings, vibrating in patterns that correspond to different particles and forces, including gravity. String theory has the appealing feature of including gravity naturally within a quantum mechanical framework, and it predicts the existence of additional spatial dimensions beyond the three we observe. But it has not yet produced experimentally confirmed predictions, and its connection to observable physics remains a subject of active development and debate. Loop quantum gravity takes a different approach, proposing that space-time itself is quantized. That space has a discrete structure at the smallest scales, below which the concepts of distance and direction lose meaning. In this framework, geometry is made of finite, indivisible units, rather than being a continuous smooth fabric. Loop quantum gravity has the advantage of not requiring extra dimensions and of maintaining the close connection to the geometric spirit of general relativity. But it is mathematically less developed than string theory and also lacks confirmed experimental predictions. The information paradox, raised by Hawking's prediction that black holes emit thermal radiation, remains one of the most debated questions in theoretical physics. Quantum mechanics requires that information, the precise description of a physical system, is never truly destroyed. But if Hawking radiation is purely thermal, carrying no information about what fell into the black hole, then the information encoded in the infalling matter is permanently lost when the black hole evaporates. This seems to violate quantum mechanics. Various proposed resolutions exist, involving holographic principles, firewalls, at the event horizon, or non-local quantum effects. But none has been definitively established. Einstein himself spent the last 30 years of his life working on what he called the unified field theory, an attempt to combine general relativity with electromagnetism into a single, unified mathematical framework. He pursued this goal with great persistence and without success. The physics community eventually concluded that his approach was fundamentally on the wrong path, that the unification of the forces of nature would require quantum mechanics as an essential ingredient, and that a classical unified field theory of the type Einstein sought was not the answer. His failure on this project is sometimes described as a tragedy, a great mind spending its final decades on an impossible task. But it might equally be seen as an illustration of the scale of the challenge. The unification of the fundamental forces of nature remains an unsolved problem today. The frontier where general relativity meets its limits is also the frontier where the most fundamental questions in physics live. Questions about the nature of space, time, and matter at their most basic level, about the origin and fate of the universe, about whether the singularities inside black holes represent physical realities or mathematical symptoms of an incomplete theory. These questions are being pursued actively with new theoretical ideas, new observations from gravitational wave detectors and the Event Horizon Telescope, and new precision experiments testing the foundations of both general relativity and quantum mechanics. The story of relativity is not finished. We have traveled a considerable distance tonight, from the patent office in Bern, where a young examiner spent his days evaluating inventions and his evenings thinking about light, through the two postulates of special relativity and the strange consequences that follow from them, the slowing of time, the shortening of space, the equivalence of mass and energy, through Minkowski's spacetime and the block universe it implies, through the equivalence principle and the realization that gravity is the curvature of spacetime itself, through the field equations and the Schwarzschild radius and the event horizon, through a century of experimental confirmations, from the bent starlight of Eddington's eclipse to the chirp of merging black holes detected by LIGO, through the expanding universe and the unresolved frontier where general relativity meets quantum mechanics. There is nothing left to explain tonight. This final section asks only that we rest for a moment in the quiet significance of what has been described. Consider what the equations of general relativity actually are. They are 10 interrelated differential equations written by one person, working largely alone, using pencil and paper, in the years between 1905 and 1915. These equations describe the formation of black holes, objects not confirmed to exist until decades later. They describe gravitational waves, not detected until a full century after the prediction. They describe the expansion of the universe, a fact unknown when the equations were written. They describe the bending of light around massive objects, the slowing of time in gravitational fields, the precession of Mercury's orbit, the existence of neutron stars, the structure of the cosmic microwave background, and the accelerating expansion of the universe. Every single one of these predictions has been confirmed by observation. Not one has been found to be wrong. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. This observation carries a particular weight When considered alongside the theory he developed, the universe is not obligated to follow rules that can be written in mathematical equations. It is not required to be organized in a way that human minds evolved to navigate a world of moderate speeds and moderate masses can understand. And yet it is. The same equations that describe the orbit of Mercury describe the structure of the universe. The same principle that explains why GPS clocks must be corrected also explains why light bends around the sun. The universe is, in some deep sense, unified. And relativity is one of the clearest expressions of that unity. The block universe that emerges from special relativity has a quality worth sitting with quietly. In four-dimensional space-time, the past, the present, and the future all exist simultaneously as a static geometric structure. What we experience as the flow of time, the sense of moments passing, of now moving inexorably forward, may be, in some sense, a feature of our particular path through this geometry, rather than a fundamental feature of the universe itself. The moment you are experiencing right now, this precise instant, exists in space-time as surely as any past moment you remember and any future moment you anticipate. It is there, fixed in the geometry of the universe, as real as anything that has ever been or will ever be. Consider the photon of light. A photon emitted by a star 1 billion light years away and absorbed by a telescope on Earth has, from its own perspective, experienced no time at all. Its emission and its absorption are simultaneous events from its reference frame. The billion-year journey that we measure, that we calculate, that we use to reason about the early universe, the photon knows nothing of it. It was created and it was detected. And between these two events, from the photon's point of view, no time passed. The universe is ancient and vast, and light crosses it in an instant. When you look at the night sky and see the stars, you are always looking into the past. The light from the nearest star beyond the sun left that star more than 4 years ago. The light from the Andromeda galaxy, the nearest large galaxy to our own, left it approximately 2.5 million years ago. The most distant objects visible to the naked eye on a clear, dark night sent their light toward you billions of years before Earth existed. You are not seeing the universe as it is. You are seeing a mosaic of different moments, each moment separated from you by the time it took light to cross the distance. The relativistic structure of space-time is part of why this is so. Light speed is finite, the universe is vast, and the two facts together mean that observation is always a form of memory. Gravity, too, propagates at the speed of light. If the sun were to suddenly disappear, Earth would continue in its orbit for 8 minutes and 20 seconds before the gravitational signal of the sun's absence reached us, traveling outward at 300,000 kilometers per second, like every other change in the state of the universe. Newton assumed gravity acted instantaneously across any distance. Einstein showed it does not. The universe enforces its speed limit on everything. The theory of relativity is, at its heart, a theory about the relationship between observers. It asks what different observers, moving at different velocities, in different gravitational environments, at different altitudes, will measure when they study the same events. And it answers, their measurements will differ in specific, calculable ways. But underlying those differences is a deeper structure that is the same for all of them. The speed of light, the space-time interval, the laws of physics. These are the things that do not change. These are the constants of the relativistic universe, the invariants that make the diversity of measured values comprehensible as expressions of a single underlying reality. Rest well. The universe is curved, time is flexible. The speed of light connects everything, and somewhere in the geometry of space-time, this moment exists alongside all the others, permanent, precise, and part of a universe that rewards careful thinking with genuine understanding.